Yes. See, in proton NMR, okay, how many signals we get for this compound, that is adamantane? Yes. Try to answer this question. How many signals we get in the proton NMR spectrum of adamantane? Yes. For this compound, we get 2 signals because this compound has 2 different types of protons. These protons attached to CH2 carbon, right? So this is, suppose see here we have 2 hydrogen, they are equivalent, right? Similarly, we have 2 hydrogens here, 2 hydrogens here, 2 hydrogen here, right? And 2 hydrogen here, 2 hydrogens, yeah, 2 hydrogens here, then we have 2 hydrogen here. All these hydrogens are equivalent and they'll give 1 signal. Okay, they are all equivalent, they'll give 1 signal. Similarly, we have the protons attached to the tertiary carbon. Okay, so this carbon has 1 hydrogen, this carbon has 1 hydrogen, this carbon has 1 hydrogen, and this carbon has 1 hydrogen. These 4 hydrogens, they are in a different environment and they are all equivalent and they'll give 1 signal. So altogether we get 2 signals in the proton NMR spectrum of adamantane. Okay, now, yeah, how many signals we get for this compound in the proton NMR spectrum? Okay, how many signals? If I take proton NMR spectrum of this compound, how many signals we get? Yes, for this compound we get 3 signals, you are right. Because there are 3 different protons attached here. See, methyl proton, let me take it as A, and the protons attached to ortho position, right? Ortho with respect to methyl, these 2 protons are equivalent. Let me represent that as B. And we have a proton at the para position. Let me represent that para position as C. The proton NMR spectrum of this compound, we get 3 signals. Actually, this question is asked in previous year GATE examination. Okay, but instead of the structure, they have given the IUPAC name of the compound. Can anyone tell me what's the IUPAC name of the compound? Yes, this compound is called 3,5 dibromotoluene. Okay, right. Now, yeah, let me ask another question. Try to answer this. How many signals we get in the proton NMR spectrum of this compound? Yes, try to answer this question. How many signals we get in the proton NMR spectrum of this compound?
1 signal, sir.
Yes, you are right. So the answer is 1 signal because it has 4 hydrogen and all the 4 hydrogens are equivalent, right? All are equivalent. It's chemically equivalent. So they give 1 signal, right? Yeah. Now, let me ask a few more questions. Try to answer this. Yeah. How many signals we get in the proton NMR spectrum of this compound? Yes, this compound will show, it shows, okay, 3 signals in the proton NMR spectrum. What are they? Listen, in this carbon, 1 hydrogen which is above the plane, the other hydrogen is below the plane. It is called exo hydrogen and this is called endo. Similarly, this carbon also has an exo hydrogen and an endo hydrogen. Okay, exo hydrogens are equivalent, HA. Similarly, here also we have HA. Here also we have HA. Exo hydrogens are equivalent, and endo hydrogens attached to each of these carbon, they are also equivalent. So we have one set of exo hydrogens, 4 hydrogens, and we have 4 endo hydrogen, they are all equivalent. And here we have 2 hydrogen, they are equivalent. These 2 are equivalent. So we have totally 3 different types of protons, okay, in this compound, right? Now let me give one more question. Try to answer this. Yeah, try to answer this question. You may be knowing the name of this compound. This is called cis-decalin. Cis-decalin, and this is called trans-decalin. Yes. See, for this compound, in cis-decalin, due to ring flipping, fast ring flipping, axial hydrogens and equatorial hydrogens, okay, on average, they behave like same. Okay, on average, axial and equatorial hydrogen, they behave like same. Therefore, in cis-decalin, all the protons are equivalent. Due to fast ring flipping, all the protons are equivalent. So we get one signal for cis-decalin in proton NMR spectrum. Whereas trans-decalin, you all know that trans-decalin is a rigid molecule where the axial hydrogens, right, and equatorial hydrogens. So let me take this axial and this equatorial. Axial hydrogens are equivalent, they'll give one signal, and equatorial hydrogens are in different environment, okay, and all equatorial hydrogens are equivalent, they'll give another signal. So for trans-decalin, we get 2 signal in the proton NMR spectrum of the compound. Okay. Yeah, I'm sorry. Actually, for this we get 4 signals. We get 4 signals, I'm sorry. Right? Because exo hydrogens are equivalent, they'll give one signal. Endo hydrogens are equivalent, they'll give one signal. And the bridgehead hydrogens, right? This bridgehead hydrogen, let me represent this as D. These 2 are equivalent, they'll give one signal. And these 2 hydrogens which are the CH2 carbon of the top, okay, they are in one environment and they'll give one signal. So for this compound we get 4 signal. Okay, sorry, please change it. Right? Yeah. Tell me how many signals we get in the proton NMR spectrum of each of these compounds. Okay. Yes, try to answer these questions. Yes, in the proton NMR spectrum, all the protons are equivalent. So for each of these compounds, we get one signal in the proton NMR spectrum. Right? Let me give a few more questions so that you can understand this clearly. Try to answer this question. For this compound, right, how many signals we get in the proton NMR spectrum? Yes. Compound in which the exo hydrogens are equivalent. We have 4 exo hydrogens which are represented as A. They are all equivalent. They will give one signal. And the endo hydrogens are represented as B. All endo hydrogens are equivalent. They will give one signal. Then the bridgehead hydrogen, they are equivalent. I represented them as C, and that give one signal. Then in the top 2 CH2 carbon, okay, the hydrogens which are present in the right hand side, they are in one environment, and the hydrogen present in the left hand side are in different environment. So D will give one signal and E will give one signal. So altogether we get 5 signals for this compound in the proton NMR spectrum. Okay. Tell me, for this compound, how many signals we get in the proton NMR spectrum. Let me draw the structure, just check it. Normally we draw like this, right? 2-methyl group, and here a keto group, correct? Correct. Now, listen, this system you can draw like this. Here we have 2 methyl groups and we have a keto group here. Yes, for this compound, how many signals we get? So here, listen, we have exo hydrogen and endo hydrogen here. They are in different environment. Okay, so HA, HB, and they are close to this. They are different actually. And we have a proton here HC and a proton here HD. They are in different environment because we have carbonyl group which gives electron pulling effect, okay, or inductive effect, right? And these hydrogens, right, exo hydrogen, let me represent this as E and this as F. They are far away from carbonyl group, and Hg and Hg, right? And these 2 methyl group are also different. Hello, are you able to follow? Hello?
Yes, sir.
GHIJ, yes. How many different types are there? Yeah. So I just represented with the different notations here. If you count them, we get totally 10. Okay, 10. So spin splitting. Listen. Spin of one nucleus and spin of another nucleus which are present in a molecule, they interact either through covalent bond or through space, okay, such that they couple each other. Because of that coupling, sometime splitting of signals may happen. This is what we call a spin splitting. I repeat, spin of one active nucleus and spin of another active nucleus present in a molecule, okay, they interact, they couple either through covalent bond or through space, okay, spatially they may interact, okay, so that the energy levels of these spin states get changed. Sometime it leads to splitting of signals, okay, signals get splitted so that you will get what are called peaks, okay. This is what we call as spin splitting, right? So in spin splitting, remember there are 2 types. What are they? One is called scalar coupling. The other one is called dipolar coupling. Scalar coupling and dipolar coupling. First we'll discuss about scalar coupling, then we'll discuss about dipolar coupling. Okay, right, what is scalar coupling? Right, listen, in most books, right, and or in most lectures, if you see, under spin splitting, they discuss the scalar coupling. Okay, so what is scalar coupling? Scalar coupling, it occurs through covalent bonds. This is the first point. Scalar coupling is the coupling between 2 active nuclei. Okay, they couple through covalent bond. And remember, spin of one nucleus couples with the spin of the other nucleus through covalent bond. This is what we call a scalar coupling, right? Scalar coupling is also spin splitting, right? Then this is very, very essential point. Keep this in mind. Non-equivalent nuclei. See, one nucleus and the other nucleus, right? Suppose they appear in different chemical shift. Observe carefully. If 2 nuclei in the NMR, they are active and they give signals in the NMR spectrum. Okay. Suppose if their chemical shifts are different, then We call them as non-equivalent. Non-equivalent nuclei couples. Okay, they interact. Isn't this coupling may leads to splitting of the signal. Right? This is what we call as scalar coupling. Non-equivalent nuclei couples so that splitting of signal occurs. Remember, equivalent nuclei, that is nuclei having same chemical shift. Equivalent nuclei also couple, but they do not split the signal. Observe carefully, very important. Non-equivalent nuclei couples, the energy levels of the spin state get changed so that splitting of signal may happen. If the nuclei are equivalent nuclei, they also couple. The energy levels get shifted, but the signal, number of signals or signal remains same. They do not, the signals, okay, do not split. Okay, this is very important. Then, spin-spin splitting, specifically in scalar coupling, occurs only between non-equivalent protons, in the case of proton NMR spectrum, okay, on the same carbon or adjacent carbon. Observe carefully. Spin-spin splitting occurs only between non-equivalent protons which are present on the same carbon or adjacent carbon. See, suppose assume that there are two protons which are attached to same carbon. We call this type of proton as geminal. Geminal protons, okay, they may couple. Or protons present on adjacent carbon, it is called vicinal. Vicinal hydrogens also couple. If the distance between, see, hydrogen attached to this carbon and the adjacent hydrogen, not adjacent, another hydrogen is attached to a different carbon. Now between them, how many bonds are there? See, there are 4 bonds. If there are more than 3 bonds, isn't here we have 3, correct? 1, 2, 3. We have 3 bonds between the two hydrogens. Here we have only two bonds. If the 2 hydrogens are separated by 2 bonds or 3 bonds, then the coupling will occur and splitting of signals may occur. If the distance increases, or if the number of bonds between the 2 hydrogens is more than 3, then the coupling effect will be negligibly small. Okay, so this coupling, right, is very, very negligible. We need not see them. We need not focus on them. Okay, so we are going to focus only on these geminal coupling and the vicinal coupling very specifically. Okay, this 1,4, this is actually called 1 bond, 2 bond, 3 bond, 4 bond, right? So this 4 bond separation, this coupling, sometime it is important. Okay, we will discuss that under separate heading. Okay, so right now we are going to focus on these two, geminal coupling and vicinal coupling. Okay, see, in NMR often we use these two words, NMR signal and NMR peaks or lines. What is meant by NMR signal? Listen, the protons, right, equivalent protons which absorb the radio frequency radiation and gives a signal, right? A group of protons, they absorb the signal, they absorb the radio frequency radiation and gives a signal, right, at a particular position, right? So what is my NMR signal? NMR signal is the entire absorption due to a particular kind of proton, protons. This is what we call as NMR signal. Okay, suppose I have methyl group. The 3 hydrogens present in the methyl group they'll give, they absorb at one particular radio frequency radiation, and they'll give one signal. Okay, what is meant by peaks? Listen, due to spin-spin splitting, the signal that we obtain for a particular group of proton, gets splitted up. Okay, and splitting of the signal gives what are called peaks. So what are peaks? NMR peaks? NMR peaks are contained sorry, NMR peaks are contained with a signal. Observe carefully, it is contained with a signal. One signal, if it splits into two, we call that as a doublet. If one signal is split into three, we call that as a triplet. Okay, so what is meant by a doublet? We say the doublet. What is meant by a doublet? A doublet constitutes one signal. A doublet constitutes one signal that is split into two. That's the meaning. If one signal split into two, we call those two. After splitting, we get two peaks. Okay, each one is called a peak. Okay, so listen, equivalent protons, they absorb at one particular radio frequency and give one signal. Due to the adjacent carbon or hydrogen present on the adjacent carbon, this signal split into many. If it is split into two, it is called doublet. If the signal is split into three, it is called triplet. Like that, we have many splitting patterns. They are all called peaks. Okay, for example, see here, I have a proton HA attached to a carbon, and there is no adjacent proton here in this case. Therefore, I'll get one signal for the proton A, one signal. Okay, so this is TMS. So we get one signal in the proton NMR spectrum of the compound. We plot intensity in the y-axis and chemical shift value we plot in the x-axis. Okay, for TMS, chemical shift is 0. Suppose in this compound, if the adjacent carbon has another proton HB, okay, HB also active. See, this is also an active nucleus. So what it will do? It will split the signal of HA into two. Okay, so HA gives one signal. Observe, okay, one signal for HA. HA gives one signal. That signal is split into two peaks. Okay, see, HA signal is split into two peaks due to the adjacent proton. Okay, so listen carefully. Different spin states of HB proton interact with the HA proton through chemical bond and then split the signal of the HA proton. See, HA proton will give one signal. That signal is split into two. Why? Because the HB proton, it has two spin states. Okay, I have one HB proton. So that proton has two spin states, alpha and beta. Okay, listen, alpha state, you know very well, it is reinforced with the external field. Beta state is the one where the magnetic field generated, secondary magnetic field generated by the electrons or by the nucleus of HB, okay, that will oppose the external magnetic field, right? So because of that, the HA proton, right, it sees two different types of signals. Okay, what is meant by that? Let me explain. Next page. See what I am trying to say here. Okay, so first I'll finish off this, then I'll explain. Listen, so HB proton has two spin states, alpha and beta. Since it has two different spin states, HA proton signal is split into two. and the intensity ratio of these two signals, these two peaks, one signal split into two peaks. And what is the intensity ratio? Intensity ratio is 1:1. We need to explain all these things, why this signal is split into two, okay, and why we get 1:1 ratio of the intensity. Okay, we'll discuss everything. Now, we have other possibilities also, right? Suppose I have the HA proton attached to one carbon. If the adjacent carbon has two equivalent protons HB, okay, I have two equivalent protons HB. Now what will happen? The signal of HA is splitted by these two protons. Okay, so I have two protons now. These two protons split the signal of HA into a triplet. Okay, and the intensity ratio is 1:2:1. Okay, now let me explain why this actually happens. What is the reason? And how does it happen? Okay. Listen. The reason is that, see, in the previous case, listen, suppose I have a proton HA which give one signal. Suppose if I have the adjacent carbon with a proton HB, see, HA and HB are in different environment. Okay, HA give one signal, HB will give one signal, but the signal of HA is split into a doublet by the adjacent proton. Why? What is the reason? The reason is that the adjacent proton HB, okay, the nucleus of this this hydrogen has two spin state, alpha and beta. Okay, so we have an alpha state and we have beta state. Now what will happen? In the external magnetic field, right, that we pass here, say B0 or BZ, right, this adjacent nucleus, the proton of HB, or the nucleus of HB, it interacts through the electrons present in the bond, and hence it interacts with the nucleus of HA. Listen, the nucleus of HB interact with the bonded electrons of here and bonded electrons of here, and then nucleus of carbon and bonded electrons here, and then it interacts with HA. Now what will happen? Since it has two different spin state, okay, the HA nucleus sees sometimes additional magnetic field, which is B0, let me write here, which is nothing but B0 plus alpha. Okay, alpha is the field induced by the nucleus, okay, and that field also reinforced with the external magnetic field, right, and the field due to beta, that will oppose the external magnetic field. Okay, so B0 minus beta. So B0 plus alpha and B0 minus beta is the field actually faces by the proton of the nucleus A. Okay, so nucleus A does not feel this effective magnetic field B0. Apart from the electrons which are present outside the nucleus, right? Apart from that, observe carefully, we have the nucleus A and surrounding electron. Nucleus A with the surrounding electron supposed to feel this magnetic field, but due to the presence of adjacent proton here, okay, there are two possibilities, alpha state and beta state. The alpha state reinforced with the magnetic field, therefore HA proton feels additional magnetic field P0 plus alpha. And in some molecule, listen carefully, in one molecule this proton may have alpha spin. In another molecule this proton may also have beta spin. Suppose if I have 100 molecule, there is a 50-50 possibility. In 50 molecule, HB protons are in alpha spin state, and HB in another 50 molecule, HB protons are in the beta spin state. Their equal probability will be there. Okay, so the molecule in which HB protons are in alpha spin state, in that case, HA proton feels more magnetic field, that is B0 plus alpha. And in molecules where HB protons is in beta state, in which the HA proton feels B0 minus beta external magnetic field. So what will happen because of that? Listen carefully. Suppose we get a signal for HA, right? In the absence of this Hb proton. In the presence of this Hb proton, now see, originally we should get a signal, we should get a peak here, but now this peak is split into two. It's split into two. Okay, and where this peak appear? This peak appears at B0 minus beta. Okay, and this peak appears at a field of I'm sorry, I made a mistake. Here it feels extra, no? 1 second. Yeah. So this is B0 minus alpha, sorry, and this is B0 plus beta. Okay. Due to the additional magnetic field, due to the spin of the Hb proton, the HA proton signal is split into two. Why? In some molecule, the HA proton feels more magnetic field. Therefore, that proton absorb at lower magnetic field, which is B0 minus alpha. Okay. And in some other molecule, this Hb protons are in beta state, beta spin state, where it will oppose the magnetic field. Since it opposes the magnetic field, the HA proton feels lesser magnetic field, lesser external magnetic field. In order to absorb, okay, it will appear, the signal will appear at little higher value. What's the value? B0 plus beta. So we get two peaks, okay, due to this reason. See, in the second example here, I have HA proton and adjacent carbon has two equivalent Hb protons. These Hb protons split the signal of HA. Right. In the absence of these two protons, HA will give one signal. But due to the presence of these two Hb, the HA signal split into three. You will get a triplet. Okay. Why we get triplet? The reason is that, see, HA and Hb protons. Hb proton may have alpha and beta spins. And this Hb proton also have alpha and beta spin. So, there are different possibilities. See, suppose if we take 100 molecules, right? In 100 molecules, listen carefully, in one molecule, both Hb protons may have alpha spin. In another molecule, this Hb may have alpha spin and this Hb may have beta spin. In another molecule, this Hb has beta spin and this Hb has alpha spin. And in another molecule, both may have beta spin. So, if you take 100 molecule, there are equal probabilities of all these spin states exist. So, we have a spin state with alpha alpha, a spin state with alpha beta, a spin state with the beta alpha, a spin state with the beta beta. Now listen, alpha alpha means they are in the same side, same direction. So, alpha plus alpha, I will get 2 alpha. This is the net spin. Alpha beta, one is in the it is in the direction of the field, and beta is the opposite, so they cancel. Here also they cancel. Here I'll get B2 beta. So what happens is that the HA proton in some molecule, the HA proton sees some additional field to alpha. It sees some additional field apart from the external magnetic field. Therefore, in some molecule, HA proton appear in lower field itself because it is getting additional field, so it appears in the lower field. How? Let me draw and show you here. See, suppose this is the position of HA proton originally supposed to present here. Now what happens? Due to this additional field faces by the HA proton, so HA proton absorb the radio frequency radiation in lower field itself, in somewhat lower field. Okay, what is the field strength? The field strength here is B0 minus 2 alpha. Okay, because 2 alpha field, extra field that HA proton is seeing. So it appears in the lower field itself. And in some molecule, there may be alpha beta spin state, and in some molecule there may be beta alpha spin state. For these two, okay, for these two spin state, the net spin is 0. Therefore, in some molecule, HA proton sees the exact magnetic field of B naught. Okay, and there are two possible spin states for this. Therefore, since there are two possible spin states, the intensity is somewhat large. Okay, and what about the other one? In some other molecule, both the protons of HB may have beta-beta spin state. Beta means they oppose the external magnetic field. Therefore, HA proton sees lesser magnetic field. Okay, since it sees lesser magnetic field, we need to apply more magnetic field, okay, to make the HA proton to absorb. Therefore, we need to apply an additional magnetic field which is equivalent to B naught plus 2 beta. This is the additional field we need to supply, okay, in some molecules. So observe carefully. Suppose if we take, say, for example, 100 molecules. In 100 molecule, not all the molecules have same spin state of HB. The HB protons may have different spin states. Okay, and this possibility, suppose I have four protons of HB. Suppose I'll take 4 molecules. In that 4 molecule, I may have this possibility, this possibility, this possibility, this possibility. Now, these two, the possibilities of these two are twice compared to the possibilities of these. Correct? This is one number, but these two are 2 numbers. Therefore, more number of molecules, right, may have these spin states. That's the reason why that signal has higher intensity. So we get a triplet. The intensity ratio 1:2:1. Why 1:2:1? Because see, this is one spin state. Alpha alpha one spin state. Beta beta one spin state. Alpha beta beta alpha. I have 2 spin states. So that's the reason why I'll get this intensity ratio as 1:2:1. Is this clear to all? Suppose I have HA proton and adjacent carbon has 3 equivalent HB protons. Okay, in this case, HA signal splits into 4 peaks. We call this as quartet. We get 4 peaks. Okay, and what is the intensity ratio? The intensity ratio is 1:3:3:1. Now we need to give explanation for this. Why we get 4 peaks and why we get this ratio 1:3:3:1. The reason is that these 3 HB protons, okay, they are all equivalent, but the spin state need not be equivalent. In one molecule, all the 3 HB protons may have alpha, alpha, alpha. In another molecule, 2 HB protons may have alpha, alpha, one may be beta. And what is the other possibility? Alpha, beta, alpha. Beta, alpha, alpha. Alpha, beta, beta. Beta, alpha, beta. Beta, beta, alpha. Then all the 3 protons may have same spin state beta, beta, beta. So these are the different possibilities of the spin states of HB protons. Is this clear? So here the net spin is 3 alpha. Here alpha, 1 beta cancels, so we have 1 remaining alpha. Here also 1 alpha, 1 beta, 1 beta, 1 beta. Here we have 3 beta. Now listen. So the HA proton sees 4 different types of magnetic field. One is, listen, it sees some additional magnetic field of 3 alpha. Apart from the external magnetic field, it sees an additional magnetic field of 3 alpha. In another molecule, okay, the HA proton sees an additional magnetic field of alpha, so that the signal will appear in a lower magnetic field. In some other molecule, the HA proton sees some lower field compared to the compared to B naught. Right? B naught means in the absence of this proton, HA will give signal, right? That position is called B naught. In some other molecule, all the 3 spin states may be beta. In that case, the nucleus of HA feels very low magnetic field. Okay, because the 3 protons opposes the external magnetic field. So nucleus A feels lesser magnetic field. Okay, so nucleus A now feels 3 different magnetic field. That is the reason why the HA proton split into 4. Okay, listen, see in the NMR spectrum, if you take, listen, see this is the original position of HA in the absence of HB proton. Now it is split into a quartet. Why? In some molecule, HA proton feels this additional magnetic field. Therefore, this is B naught. This is supposed to be B naught, but now the HA proton absorbed in lower field itself. In lower field itself. So what is the field strength? B naught minus 3 alpha I'll put. Okay, and I have only one spin state, so the intensity will be less. And in some other molecule, listen, the molecule see a lesser magnetic, sorry, it feels an additional magnetic field of alpha, but I have 3 spin state now, so the intensity will be somewhat high. Okay, and what is the magnetic field value here? B naught minus alpha. Right? In some other molecules, right, the HA proton feels lesser magnetic field compared to B naught due to the spin of the HB proton opposes, right? The magnetic field due to spin of the HB proton may oppose the external magnetic field. Therefore, the nucleus A feels lesser magnetic field. In that case, we need to give more field to make the HA proton to absorb. And there are 3 possibilities of these spin states. So we get a ratio like this. Then I have one more. Okay. So this corresponds to B naught plus beta. And this corresponds to B naught plus 3 beta. Okay. So HA proton sees 4 different magnetic field strength. Okay. In one molecule, it feels this strength. In another molecule, it feels this strength. It feels this strength. This feels this strength. Okay, and why the ratio is 1:3:1? Because see, this spin state is only one, whereas this spin state is 3, and this spin state is 3, and this spin state is only 1. So we get 1:3:3:1 ratio. So in general, if I have an HA proton, it gives one signal. See, if there are n equivalent protons of HB present in the adjacent carbon. See, I have HA proton which will give one signal. In the adjacent carbon, suppose if I have equivalent, right? Equivalent HB protons. Okay, the protons attached to this carbon, so they may be equal. If the protons are equivalent, if I have suppose n equivalent protons, what it will do? It will split the HA into n plus 1 peak. Why n plus 1? The reason is that actually number of peaks, this is the formula. Number of peaks is equal to, if the protons are equivalent. If the protons present in the 2 carbon are equivalent, the number of peaks equal to 2ni plus 1. This is the formula. Okay, so 2 into, I'll keep this n as such. I value for proton is half plus 1. So this two cancel each other. So we get n plus 1 peaks. Okay, so if I have HA proton, if the adjacent carbon has n equivalent HB protons, then the signal of HA split into n plus 1 peaks. Okay, if n is 0, suppose if adjacent carbon has no HB hydrogens, HB protons, in that case we get only one signal. We can also say that it is singlet. You get one signal mean one peak. One signal mean one peak is called singlet. And the intensity is 1. Suppose if n is equal to 1, if adjacent carbon has 1 HB, in that case, it will split the HA signal into 2. You will get a doublet. And the intensity ratio is 1:1. If you have 2 hydrogens HB, 2 hydrogens of HB, then I will get a triplet. The ratio is 1:2:1. Then we get quartet, quintet, sextets, depending upon the number of hydrogen present on the adjacent carbon. If there are more than 5 hydrogen present on adjacent carbon, we get what is called a multiplet. We get a multiplet structure. More than 5 hydrogen means multiplet. Okay, yes, keep this in mind, very, very important. Sorry, not more than 5, more than 6. I'll give one more in the next page. One second. Yeah. See here. So, we have, suppose if number of hydrogen and adjacent carbon is 6, we get what is called septagon. This is the intensity ratio. Okay, if you get more than 7 peaks, we call that cluster of peak as a multiplet. Okay, now to find this intensity ratio, right? To find the intensity ratio, we have shortcut. We can use what is called Pascal triangle, which is actually constructed using binomial theorem. Okay, I'm not going to discuss binomial theorem. Instead, I'm going to give you what is called the Pascal triangle. Okay, listen carefully. This is very, very important. If this Pascal triangle is applicable for NMR active nucleus having I value of. Okay, if I value is 1 or 3 by 2 or etc., then we have what is called non-Pascal triangle. Okay, I'm going to give you Pascal triangle now. Okay, now listen. See, n is equal to n plus, we get n plus 1 peak, right? A signal is split into n plus 1 peaks in the case of proton NMR. Okay, our adjacent adjacent carbon has protons. If I put n is equal to 0, I'll get 1 peak. So we start with 1. Okay, so I have intensity of 1. Now to find the intensity of the next, what I'm going to do, add 2 zeros because I have number 1 here. So add 2 zeros both sides. So let me add 2 zeros both sides. Now what to do? Add the 2 numbers. First 2 number and the next 2 number. See what I'm trying to say? Add these two. 0 plus 1 is 1. Then add these two. 1 plus 0 is 1. So we get 2 signals in the intensity ratio 1:1. Okay, this is n is equal to 0. If there is no hydrogen on adjacent carbon, we get only one signal and it is called singlet. If adjacent carbon has 1 hydrogen, then it is then that hydrogen split the HA proton into 2. You get a doublet. To find the next, for the next that is for triplet, this is for doublet. For triplet, what to do? Add 2 hydrogen both sides, then add 2 numbers each. Okay. First I'll add these two. 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 0 is 1. So we get signals with the intensity ratio 1:2:1. This is for singlet. This is for doublet. And this is for triplet. Okay. So this is for n equal to 2. If n is equal to 2, we get triplet. Remember, n is nothing but number of Hb protons present on the adjacent carbon. Okay. Suppose I want to know what is the intensity ratio for n is equal to 4. I'm sorry, n equal to 3. 3. What to do? Add 2 zeros both sides. Then sum up. Okay, as usual. Right? How? Add these two. 0 plus 1 is 1. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 0 is 1. Okay, so intensity ratio is 1:3:3:1 for quartet. Okay, if n is equal to 4, then add 2 zeros both sides. In a similar manner we have to follow. Add 2 zeros both sides, then add 2 numbers each. Okay, so suppose if I add these 2 numbers, I'll get 1. If I add these 2 numbers, I'll get 4. 3 plus 3, 6. 3 plus 1, 4. 1 plus 0, 1. So we get the intensity ratio as 1:1:4:6:4:1. This is for quintet. Okay, like that we can find the intensity ratio of any peaks in this manner. Okay.